How to read a P&ID. That is what this video covers. Walk into any process plant, and someone will hand you a drawing covered in circles, diamonds, bubbles, and lines. That drawing is a piping and instrumentation diagram. Every process plant on Earth uses them. The electrician reads wiring schematics. The mechanical engineer reads isometrics. The controls technician reads P&IDs. If you cannot read one, you are guessing at how the process works. This video teaches you to read them, what the symbols mean, how the ISA letter codes decode to real instruments, how to follow a single control loop from the field device to the controller and out to the final element. By the end, you will trace a flow transmitter to a flow controller to a control valve without guessing. Start with what a P&ID actually is. It is not a layout drawing. It does not show you where the pipes are physically located in the plant. It shows you the functional relationships between process equipment, piping, and instrumentation. Three families of information live on a P&ID. First, the process equipment. Vessels, heat exchangers, pumps, compressors, reactors, drawn as simplified geometric shapes. A vertical cylinder is a column. A horizontal oval is a vessel. A circle with a triangle inside is a centrifugal pump. Second, the piping. Lines that connect the equipment. Line weight and line style tell you whether the pipe carries process fluid, instrument signal, electrical signal, or pneumatic signal. A thick solid line is a main process pipe. A thin solid line is an instrument impulse line. A dashed line is an electrical signal. A dotted line is a pneumatic signal. Third, the instruments. Circles, bubbles, and diamonds mounted on the piping or the equipment. Each instrument bubble has a tag number that tells you exactly what the instrument measures and where it lives. Learn the instrument bubble and the tag code system, and you have the key to every P&ID. Line types first. A thick solid line carries process fluid. This is the pipe you would actually touch in the plant. A thin solid line connected to an instrument is an impulse line. It carries process fluid to the instrument sensing element. A dashed line carries an electrical signal. This is the wire from a transmitter back to a controller. A dotted or dashed dotted line carries a pneumatic signal. This is the compressed air signal from a positioner to a valve actuator. In some standards, the pneumatic line is a long dash short dash pattern. Check the drawing legend on the first page. Every P&ID has a legend sheet. Read it before you read any other sheet. Equipment symbols are standardized by ANSI and ISA, but every company adds their own legends. Pumps are circles or half circles. Vessels are rectangles or cylinders. Heat exchangers are tubes in shell symbols. Valves are bow tie shapes on the line. A gate valve is a bow tie. A ball valve is a circle inside the bow tie. A globe valve is a small triangle. The physical size of the symbol tells you nothing about the physical size of the equipment. The symbol just identifies the type. Now the instrument bubble. This is the most important piece of the P&ID. An instrument bubble is a circle, usually about 10 millimeters in diameter on a printed drawing. It sits on the piping or connected to the equipment by an impulse line. The bubble is divided by a horizontal line. Above the line is the tag number. The tag number has two parts. Letters first, numbers second. The letters are the ISA letter code. The numbers identify which loop the instrument belongs to. The ISA letter code works like this. The first letter is the measured variable. F is flow. P is pressure. L is level. T is temperature. A is analysis. D is density. The remaining letters are the function. T means transmitter. C means controller. V means valve or control valve. I means indicator. A means alarm. E means sensing element. So FT101 means flow transmitter 101. PT203 means pressure transmitter 203. LC105 means level controller 105. FC101 means flow controller 101. The number usually ties together all the instruments in the same loop. Flow transmitter 101 feeds flow controller 101, which drives flow control valve 101. When you see the same number on three different bubbles, you have found a complete control loop. The horizontal line inside the bubble tells you where the instrument lives. No line means the instrument is in the field. A solid horizontal line means the instrument is on the control panel, visible to the operator. A dashed horizontal line means the instrument is in the distributed control system, the DCS, not on a physical panel. Here are the letter codes you will see most often. First letters for measured variable. F is flow, P is pressure, L is level, T is temperature, A is analysis. That covers pH, conductivity, oxygen, and composition analyzers. D is density. S is speed or frequency. Z is position, used for valve position feedback. Second and following letters give you the function. T is transmitter. The transmitter sends a 4 to 20 milliamp or digital signal to the controller. C is controller. It receives the process variable, compares it to the set point, and calculates the output. V is valve. I is indicator. Y is a function block or relay used for computation or signal conditioning. A is alarm. H is high. L is low. HH is high. LL is low. So FAH means flow alarm high. LAL means level alarm low. These are your safety layer. When you see a H or a L on a bubble, that point trips an alarm. It fires when the process goes out of bounds. Now read a real loop end to end. Take a pump discharge flow control loop. The process pipe leaves the pump. A flow element, tagged FE101, sits in the pipe. The flow element is the orifice plate or the vortex meter or the magnetic flow meter, the primary sensing device. A small impulse line runs from the flow element up to a flow transmitter, tagged FT101. The flow transmitter converts the differential pressure or the vortex pulse or the electromagnetic output into a 4 to 20 milliamp signal. A dashed line, an electrical signal line, leaves the transmitter and runs off the drawing edge toward a DCS input card. The flow controller, FC101, lives inside the DCS. Its bubble has a solid horizontal line, indicating a panel or a DCS faceplate instrument. Another dashed electrical line carries the controller output back to the field. It connects to a flow control valve positioner, tagged FY101. The positioner is the signal converter sitting on the valve actuator. It receives the 4 to 20 milliamp controller output and converts it to a pneumatic signal. A dotted line then runs from the positioner to the valve actuator. The valve actuator drives the valve stem. The valve is tagged FCV101. On the drawing, it is a bow tie with a circle on top, indicating an actuator. This is one complete loop. Transmitter to controller to positioner to valve. Every flow, pressure, level, and temperature control loop on the drawing follows the same pattern. Common mistakes when reading P&IDs. First mistake: confusing the tag number with the loop number. The tag number on the bubble identifies the individual instrument. The number portion identifies the loop. FT101 and FC101 are different instruments in the same loop. This gets confused when there are multiple instruments with the same number but different first letters. They are always in the same loop. Second mistake: missing the line type. A solid line on the drawing that looks like a process pipe might be a small bore instrument impulse line. The line weight is the clue. Always check the legend for line weight conventions on that specific drawing set. Third mistake: assuming the bubble location equals the physical location. A bubble with a solid horizontal line means the instrument is on a panel. It does not mean the panel is near the pipe shown on the drawing. Panels can be across the plant in a control room. The P&ID shows logical connections, not physical distance. Fourth mistake: ignoring the diamond symbols. A diamond bubble means a computer function, usually a DCS or PLC calculation point. FY101 inside a diamond is a signal selector or calculation block inside the controller, not a physical field instrument. These are software objects. Fifth mistake: stopping at the P&ID. The P&ID gives you the instrumentation picture. The cause and effect matrix gives you the safety layer. The data sheets give you the instrument range and calibration. Use all three together. Practice reading P&IDs at plcsimulationsoftware.com. The drawing lessons are free. You will get a real P&ID fragment. Find the tags, trace the loops, and get immediate feedback on whether you identified the loop correctly. This is faster than trying to learn from a static textbook diagram because the simulator tells you when you are wrong and shows you why. Link is in the description. If this helped you decode your first P&ID, subscribe. The next video covers cause and effect matrices. That is how you understand what shuts the process down when something goes wrong. See you in the next one.